Hey Chem30s, Manchak here again with your final video for our work through concepts B7 through B9. And so far you should have covered a quick introduction video that got you started on concept B7 and sort of set the stage for these three concepts. Then you worked your way through some worksheets, voltaic cells video, that had you introducing to you what voltaic cells are, how to draw them, those kinds of things. Then you should have done a video, pardon me, on cell potentials, which would have walked you through how to calculate cell potentials. And along the way, you should have done a couple of LSM worksheets to give you some practice with both voltaic cells and with calculating cell potentials. Where we are at with this video is I'm going to be walking you through, I've just got some notes here to remind myself of things to say. This one is going to walk you through electrolytic cells, which you can see on the main part of the screen right now. And then I'm going to take a couple of minutes to talk to you about concept B9 and what B9 is all about. I think I introduced that to you back in the introduction video, and the fact that the B7 through B9 can be a little bit foggy because we kind of, B7 circles back. I do voltaic cells, then we do cell potentials, then I'm coming back to electrolytic cells, which is still also part of B7, and then B9, which we'll talk about in a minute here, is that similarities and differences between electrolytic and voltaic cells. So we're going to get into this right here. It should be a relatively quick lesson, I think, because you should have everything more or less down after covering everything you've done with voltaic cells and cell potentials so far. Before I get into this, I just want to refresh your memory on a couple of things that I think are important for you to be aware of and to have in the front of your mind. Remember, through this whole unit, we've been talking about Leo goes Gur. So loss of electrons is oxidation, gain of electrons is reduction. Okay, and I've always said to you, not only do you need to memorize that mnemonic, but you also need to understand what it means. What's the meaning behind it? What does it mean to be oxidized? What does it mean to be reduced? And then for the last little bit, we've been focusing on strongest oxidizing agent gets reduced at the cathode, and the strongest reducing agent gets oxidized at the anode. So S, I'm going to really poorly draw on my trackpad on my MacBook here. So SOA, strongest oxidizing agent, gets reduced at the cathode. Okay, and the strongest reducing, oh boy, agent, SRA, gets oxidized at the anode. And I've told you this before, but those two things, Leo goes Gur, and these bits right here, those are really one of the most important things you need to understand for this unit, to really get and understand what we're doing here. So try to not only memorize those, but really try to understand the meaning behind them and what's encompassed in them. So we're going to circle back to these two things up here again as we move our way through the rest of the unit. So we're circling now back to B7 to talk about electrolytic cells. I've warned you already that we're going to talk about two kinds of electrochemical cells. We're talking about voltaic cells and we're talking about electrolytic cells. I want you to understand, and I've said this before and I'm sure I'll say it again, is that a voltaic cell and electrolytic cell are not opposite to each other. They are different from each other, but they are not opposite to each other. And B9 is going to go in and highlight those similarities and differences between the two that I think are important for you to understand. We're also going to tie back in some reduction potential stuff and some cell potential stuff in this section too. So let me introduce you to electrolytic cells, and this will be a bit of a review of some voltaic cell stuff, which is good if you haven't watched that first voltaic cell video recently. So recall that in a voltaic cell, electricity is produced, and that word produced is important. Okay, it's a spontaneous reaction because each half cell contains both oxidized and reduced entities. So the cell potential in or E cell in a voltaic cell is greater than 0, and the strongest oxidizing agent is always above our strongest reducing agent in our table of relative strengths that we have on page 7 of our data booklet. Okay, so we remember back from concept B3 that if your strongest oxidizing agent is above your strongest reducing agent on your table, I suppose I should do it this way because it'll make more sense to you. Strongest oxidizing agent is above your strongest reducing agent on your table. Then you have a spontaneous reaction. If we have a spontaneous reaction, we are dealing with a voltaic cell. In electrolytic cells, some of this is opposite. Okay, but they still operate in the same way. So we're going to get to that. So please don't walk away from this thinking voltaic and electrolytic are opposite. They're not. There are some things that are opposite, but there are also some things that are very similar between the two. So in electrolytic cells, the reaction is non-spontaneous. So that's opposite to voltaic cells. There's a difference for you. The strongest oxidizing agent is below the strongest reducing agent on our tables. Well, this is hard to do when you're doing it on a screen and everything's backwards. So strongest oxidizing agent is below the strongest reducing agent, and our cell potential is less than 0. In electrolytic cells, because of these factors, they do not produce their own electricity, right? We said up here that voltaic cells produce their own electricity. In fact, what happens is that electrolytic cells require energy. And if you think about it for a second, that should make sense. Because if it's a non-spontaneous reaction, think about that for a second. If you hook the whole thing up, like you would a voltaic cell, ain't nothing going to happen. So what has to happen in this case is we need to add, and just down here at the bottom, we need to add an external battery, a power source of some sort, to feed electrons into the system in order to turn that spontaneous or turn that non-spontaneous reaction on. So what you're going to see, and here's another difference. In a voltaic cell, yes, of course, we have a similarity. They both have 2 electrodes, okay? But in a, I don't know if you can hear my daughter screaming upstairs. She's being a dinosaur or a tiger or something and roaring. So we have 2 electrodes in both of these. There's a similarity, but here's a difference. In a voltaic cell, we had 2 electrolytes. One electrolyte where the cathode was dipped into, one electrolyte where the anode was dipped into. In an electrolytic cell, we only have 1 electrolyte. And both of the electrodes are dipped into the same electrolyte. Okay, and that's an important distinction. And then we talked about having the external battery. And I want to make a note here that the half cell reactions do not need to be split up. And what I mean by that is, remember, in our voltaic cell, we would have 1 beaker and another beaker with our 2 electrodes with 2 solutions, and then we would have a salt bridge between the 2. Well, in the case of an electrolytic cell, because the reaction is non-spontaneous, we can have those 2 things sitting together in the same solution, in the same beaker, and they won't react until we turn the power source on. If we did that same sort of situation with the voltaic cell, where we just use 1 beaker and 1 solution and dip them in together and hook them up, we would get a reaction, but it'd probably all take place inside the beaker, and we wouldn't really get that generation of electrons that we would want from a voltaic cell. So that's why we have to have that separation of the two electrodes, or the 2 half cells, in order to make a voltaic cell run. We don't need that with an electrolytic cell. So an electrolytic cell uses a process called electrolysis, which supplies electrical energy to force a non-spontaneous redox reaction to occur. And I think the key word here is force that non-spontaneous reaction to occur. Like I said, if we don't hook this up to a power source and switch it on, nothing's going to happen. And so the battery forces electrons to cause an electron transfer. This would be, if we read this in the forward direction, so from left to right, this would be a voltaic cell. However, if we read this in the reverse direction, from the right side to the left side, so this bottom arrow here, we would see that this is an electrolytic cell. We need to supply energy to these products. They become the reactants, in essence, to produce something as a result of this. So there is a little bit of a difference between the two going on here. I hope that kind of makes sense. Moving on here, research has indicated that the generalizations we make for voltaic cells are the same as those for electrolytic cells too. So this is the bit right here where I said, don't think of these as opposite. Okay, don't think of voltaic and electrolytic as opposite. Think of them as some things are opposite, but some things are the same. And here's the same part coming up here. The strongest oxidizing agent gets reduced still. So it attracts electrons most strongly, right? It's attracting electrons to gain those electrons to become reduced. And it gains the electrons at the cathode still. So electrons still flow from anode to cathode, and the strongest oxidizing agent still gets reduced at the cathode, and the strongest reducing agent still gets oxidized at the anode. So that is exactly the same between voltaic and electrolytic cells. Note, though, that in a voltaic cell, it does not matter where the electrons come from, whether it comes from the, or in these cells, it doesn't matter where the electrons come from, whether it comes from the battery or from the anode. It would come from a battery in an electrolytic cell, or it'd come from the anode in the voltaic cell. Electrons still flow from anode to cathode. And then, like I said just a moment ago, the strongest reducing agent still loses electrons and gets oxidized at the anode. However, here's another little difference, and I've got a summary table I'll show you at the end with all of these differences and similarities. Note, in an electrolytic cell, the cathode is negative and the anode is positive, and that's different from in a voltaic cell, and that just has to do with us hooking up that power source and causing that change in polarity of the electrodes in this case. So electrons are still flowing anode to cathode in an electrolytic cell, just like in a voltaic cell. The strongest oxidizing agent still gets reduced at the cathode, and the strongest reducing agent still gets oxidized at the anode. So these are the same things happening in both. So, I gotta click to the next one here. So what I've got here is just a quick diagram of what an electrolytic cell might look like. And I chose this diagram because it also gives us a practical application to what's going on in these electrolytic cells. So notice first off that this is just a beaker, not two beakers like we had in voltaic cells. Notice that we have two electrodes, and what's interesting about this one is one electrode is a silver electrode, so that kind of makes sense. But the other one is actually a spoon. Now that's kind of cool. And I'll get to that in just a second. So the silver electrode is just solid silver, and this is some kind of a spoon. Inside this beaker that these two electrodes are dipped into, we have a solution of silver nitrate. Please remember that solution will dissociate into silver ions and nitrate ions. So we'll have silver ions floating around in this solution, and the nitrate ions, as they've always been so far, are spectators. They're completely ignored in this situation. Notice that we've got wires hooked up. So we've got a wire that connects the electrode or the silver electrode to a power source, and we've got an electrode that hooks up the spoon to the power source. You'll also notice in this situation that our anode is positive. There's a difference from those voltaic cells earlier, and that our cathode is negative. And we'll also notice that electrons are flowing from anode to cathode still. Okay, so why I wanted to point this out and why I think this is a really interesting example is there's a practical application for creating an electrolytic cell like this. And this electrolytic cell, if we let it run, what would end up happening is over here at the anode, oxidation would occur. So what would happen here is silver ions would oxidize, or sorry, solid silver atoms would oxidize into silver ions, losing an electron. That electron would move up here and along this circuit. Those silver ions then would bump up against the spoon on the other side, and those electrons that are coming in from the power source would be gained by the silver ion, and we would end up creating a piece of or a silver atom on the surface of that spoon. Every single time a silver ion bumps up against the spoon, it's going to gain an electron at the cathode, and it's going to turn into a piece of metal silver again, rather than the silver ions. And so what we are effectively doing in this electrolytic cell is we are putting silver on the outside of the spoon. This is a process we call electroplating, and we use it to create silver spoons like we have here. We might use electroplating to put maybe gold on the outside of some electrical equipment. We might use it to chrome plate a bumper, something along those lines. But this is what an electrolytic cell would actually look like and how we would work with it. And so I want you guys to really see the difference. There's similarities in how it's set up. We've got 2 electrodes. There's a solution involved, but only one. We've got external wiring going on that's connecting the electrodes, but instead of having a voltmeter in between, we've actually got something that is creating a flow of electrons, a voltage source right in the middle here. So I hope that diagram helps you to kind of visualize a little bit what's going on with an electrolytic cell. So this table I think is very important, and what it's doing is it's giving us a comparison. Remember, comparing and contrasting, so we're looking for distinguishing between the two. This is B9 right here, okay, distinguishing between voltaic and electrolytic cells. So what is similar, what is different? And so as you work your way through this table, you're going to see similarities and differences. Here is a difference, right? Voltaic cells are spontaneous, electrolytic cells are non-spontaneous. Here's another difference. The cell potential in a voltaic cell is positive, the cell potential in an electrolytic cell is negative. Here's another, here's a similarity and a difference when it comes to the cathode. We've got the strongest oxidizing agent undergoing reduction in both. There's a similarity. Here is a difference in that the cathode is positive in a voltaic cell, negative in an electrolytic cell. In the anode, here's a similarity. Strongest reducing agent still gets oxidized in both of these. However, the anode is negative in a voltaic cell, positive in an electrolytic cell. Direction of electron movement is similar, the same in both. And then the direction of ion movement is the same in both. That ion movement, it would be what we'd be looking at in a voltaic cell, what's going on with our salt bridge and where the ions are going into and out of the salt bridge. In the case of an electrolytic cell, the anions are going towards though there's no really anodes, they really don't have anywhere to go, but the one that I like is the cations go towards the cathode. Well, there's a cation, positively charged ion, that's moving towards the cathode in this case. So that's your summary table. That's the big portion of B9 is this table right here. Okay, so I would be really spending my time to make sure I can list similarities and differences between voltaic and electrolytic cells. Just a couple other things, because I want to talk a little bit more about practical application of what's going on with understanding an electrolytic cell. So I wanted to talk about secondary cells, which actually involve the capability of being both a voltaic and electrolytic cell. And the simple way to think about these is in terms of a rechargeable battery. Okay, your cell phone has a rechargeable battery. Whatever device you're working off of right now to watch this video has a rechargeable battery. And the difference between the two things is that you've got or a regular battery is only designed to be run down until it can no longer carry a charge anymore. In other words, we've moved all of the electrons effectively over from the anode to the cathode. And that regular non-rechargeable battery, when it runs out of that ability, it's done for. Okay, rechargeable batteries allow us to run electrons from anode to cathode and generate electricity. But then when we hook those batteries up to a power source, i.e. you plug your phone in to charge it up, what happens is we run, we rebuild those two electrodes that were worn down. There was a video I showed you guys back in the voltaic, or I asked you to watch back in the voltaic cells section, where it showed what was happening at the anode and the cathode. And when a voltaic cell is running, what happens is the anode is actually breaking down. The solid electrode is losing electrons, and those electrons are flowing up into the external circuit, and we've got ions that are entering into the solution that anode is dipped into in that voltaic cell. And what happens if we were to be able to watch it, that electrode would actually slowly be eaten away as those electrons flow away across the external circuit to the cathode. What's happening at the cathode at that time is that cathode is gaining electrons, and the ions that are in the solution in the cathode half cell are bumping up against that electrode, gaining electrons and turning into solid metal at that point. And so the cathode is actually getting larger. So in a voltaic cell, the anode gets smaller, the cathode gets larger, and we end up with, in a regular battery, the anode basically disappearing, and the cathode is, all we have left is cathode. In a rechargeable cell, what we can do is we can hook it up to a power source and basically reverse that reaction. So the anode had disappeared, the cathode had got very large. When we hook it up to a power source, what used to be the cathode that got very large becomes the anode. What used to be the anode that became very small becomes the cathode. And so we end up with eating away at the new anode, right, which used to be the cathode, and adding back onto the new anode, the new cathode, which used to be the anode. And so we basically reverse the reactions, and it regenerates the cell. So that's what this is showing here. In a nickel-cadmium battery, a NiCad rechargeable battery, what's happening is when we're using the battery, in other words, we've got a situation where it's powering whatever device we have it in, we have our cadmium ions breaking down, or cadmium breaking down into ions and transferring electrons over to the nickel, and the nickel being generated into solid nickel at that point. What ends up happening then is that the electrons being transferred here, we put something in between it, the circuit that runs the whatever device we're operating. And slowly but surely that cadmium electrode breaks down and that nickel electrode gets bigger. Then, when we stop operating and we go to set that battery to charge or recharge, things switch. The cadmium electrode now starts to build its way up by gaining electrons, and it recharges into that solid cadmium again. And the nickel electrode starts to break down, whittling its size down again. Okay, so what we're doing is basically reversing what's going on. And the only difference is to cause this is that we are supplying power here, whereas we are creating power in this situation. So when we're draining the battery, making it power our electronic device, it functions as a voltaic cell. When we plug the battery into the wall to recharge, it's using the electricity from the charger, the wall socket, to reverse the reaction, creating an electrolytic cell. What this does is it recharges our battery. I should note this is not perfect. It's not a perfect reaction. It doesn't happen in such a way as to make sure that that battery can just go back and recharge perfectly every time. There's always a little bit of chaos involved. The electrodes don't reform perfectly every single time. And so what happens is eventually, and we all know this, our battery runs out of battery life. Our rechargeable battery just doesn't hold the charge anymore, just because this recharging process isn't creating a nice electrode anymore. It's creating more of a messy electrode, if you want to think of it that way. So I hope that made sense. What I'm going to do right now is I want to talk about one last thing associated with concept B9, and that's something called the chloride anomaly. And I'm just going to pop open. This is actually a page in your textbook. I should scroll down and show you. It's in section 14.3, page 645. And what this section is talking about, I'm going to move my video down here too, just so that you guys can see. It's talking about the chloride anomaly. And I'm just going to read it through and just report or talk about the thing that I think is the most important to remember about this. There's exceptions to every rule. Here is an exception. Okay. So as you know, we didn't do investigation 14.5, but some redox reaction predicted using the strongest oxidizing and strongest reducing agents from the table do not always occur in an electrolytic cell. So we're dealing with an electrolytic cell. Like other chemical processes, a half-cell reaction and an electrode has an activation energy that varies for different half reactions and conditions. Therefore, the actual reduction potential for a particular half reaction and the reported reduction potential may be different. The difference is known as the half-cell overvoltage, and it is generally much greater for the production of oxygen than for the production of chlorine. For example, in the electrolysis of aqueous chloride compounds. So here's what we do. This is what we call our chloride anomaly, and what's in italics here is what I want you guys to understand about the chloride anomaly. As an empirical rule, so empirical means when we're actually doing this in practice, in a lab situation or a real life situation, you should recognize that chlorine gas is produced instead of oxygen gas in situations where chloride and water are the only reducing agents present. So I'm going to take out my data booklet and sort of hold this up to the screen. I'll make this big and sort of show you what I'm trying to talk about here. So in our data booklets, I hope that appears as right side up. You guys will notice that we have chloride ions here, okay, and we've got water here as our two reducing agents. What this section says, and I'm just gonna reduce it again. What this section says is that chlorine gas is produced instead of oxygen gas where chloride and water are the only reducing agent present. So when we go through our table, and I know this is really hard to see, but there's the chloride ions there and there's the water there. We would normally say that water is the strongest reducing agent in this case, and therefore oxygen gas should be produced. But in actual fact, empirically, if chloride and water are your only reducing agents, then in actual fact, even though I've told you that your strongest reducing agent will be lower down on the right-hand side, what ends up happening is the chloride becomes the strongest reducing agent, and so we will produce chlorine gas instead. That's what we call the chloride anomaly. Okay, it's an anomaly. It's an exception to the rule. It's not always that the rules aren't always hard and fast, and sometimes there's an exception to them. So this bit in italics here that you guys can see on this page, that's super important. What it basically means is if you have two reducing agents, one oxygen and one chloride ions and one water, that even though water appears to be a stronger reducing agent, chloride ions will take over as the strongest reducing agent, only in that situation. Alrighty, that's it. That was a lot longer than I expected it to be. I hope this makes sense about electrolytic cells. And I hope that I've tied in B9 well enough that you understand what B9 is all about. At this point, you can jump in and go ahead and do LSM 14.3E, which is a practice worksheet on electrolytic cells. It's not the world's greatest worksheet. In fact, when you get to the bottom, the last two questions are really, really strange. They made a bunch of mistakes doing the key, so you'll notice that when you look at the key, I've scribbled out a bunch of stuff and fixed it. So go ahead and have a look at that. Do some practice on that, and try to understand those electrolytic cells a little bit better. Have a look at worksheet number 3. And get that done now. At this point, there'll be a practice assignment for B9, and if you haven't finished B7 already, which you probably can't do until you've done all of this, you can do that. The only other thing to mention is at the end of this section of notes, you'll notice that there are some fill in the blanks on the different kinds of electrolysis that we can do. Please make sure you have a look at that as well and fill them in. They're just based off of sections in your textbook, and it gives you some more examples of how we apply our knowledge about electrolytic cells to practical situations. Once you're done all of that, you can jump on and do the summative assessments when they're up and ready to go. Just remember to only do the summative assessments after I've given you feedback and you've sought help on the formative stuff. Don't just do formative and then right after go and do the summative assessments. Give me that opportunity to give you some feedback. Because we're not face-to-face, I don't get the opportunity to look over your shoulder as you're doing questions and answer questions right away. So give me that chance by giving me some time to look over your practice assignments, your formative assignments, and provide you some feedback. So that's all I have to say. I hope you enjoyed this 30 minutes. And stay healthy, take care of each other, and stay isolated. See ya.